So today we have Adam Kudutek with us from IDEA StatiCa. So I will show in the beginning a small structure where we have done a structural analysis, and then pass the computer to the presentation to Adam, and he will show how to design and verify steel details, connection details, and specifically details for membrane structures. So we're quite interested in this topic. So I think we can start. Yeah. So let's see how to enter IDEA StatiCa. You see my screen?
Yes.
Oh, fine. So we see here, this is a small high part that we have run the structural analysis. You can see we have different load cases here. In the plots, we have made the standard load cases for ultimate limit state. Okay, so we can see, for example, deformations, deformed shape, and so on. So once we have done this, this is our basic work to run the structural analysis, base it on the country codes that we are using. And clearly, one of the most generally long tasks to perform is to check the connections. Now, when we go and we design the steel, we need to check these connections and make specific connections for membrane structures. So let's see how we can do that. We have a specific connection with IDEA StatiCa that you can find here in the post-processing tools. To use it, you unhide the nodes, the FEM nodes. Clearly, the nodes that we are going to check are not the inner membrane nodes. There's no connection there. So we want to check the nodes where the steel connects the ground nodes here, where we have the mast, the cables, and the connection nodes. How do you do that? You just select a node. You recall from the post-processing, the IDEA StatiCa tool. This window pops up. Here, you just write the node, the name of the node. So this is my top mast. And you say, create edit connection. The first thing that the software does, he connects to the IDEA StatiCa checkbot. So he's loading in this moment. I have it on my other screen. Here it is. So this is the IDEA StatiCa checkbot. This is an intermediate function, intermediate software. So we see here, this is the node that we have selected. And we have to say, make a connection. And he imports the node. Okay, that's it. It was already imported. This was an old screen. He imports the node that we have selected. Now we want to enter IDEA StatiCa. And how do you do it? Here you have the tool open. So if I click on open, the checkbot opens IDEA StatiCa and enters the software with the node that we have selected. You see here we have only the elements connecting to the node with all the load cases and the result of the load cases from the structural analysis. So I think that was quite simple. Let's give it a try again so we can do it again. I want to do it, for example, for this node on the bottom of the pole. So you select the node, you recall it as StatiCa, you say this is my base mast, and you say create edit connection. So IDEA StatiCa opens the checkbot. Okay, now it started. As soon as he opens the checkbot, you have the option here to choose which code you want to use for checking the steel connection. So basically where you're doing the project, you choose one of those codes. And then you say, create project. This is how it starts, a blank screen. So with a new project, now we have to import the node. Remember, we have selected the node inside the software, inside the FEM software, and you say, I want to make a new connection. So imports this data, and you see here, this is the node that we have selected. He also imports the elements connected to that node. So if this is what you want to do, you just open it with open this connection node. Okay. and that's it. So this is a single pipe, so it's the end of the mast, and that was quite simple. So this is quite simple. You don't have to do so much. Now the hard work comes in. So I will pass to Adam the hosting. So he will show how let me find where Adam is here. Adam, okay.
Yes.
And 1 second, Adam. I'll set you to host. Okay.
All right. So
I think I have to stop my sharing, maybe.
yes, I will take the sharing. Don't worry. So let me do that. I'm gonna share my primary screen, which is this one. All right. So I hope you can see my screen and hear me clearly.
Yeah, yes. Fine.
Thank you. And once again, warm welcome from me. I'm very excited to be part of this great seminar about designing member structures with ixCube. And today I will show you the part how to deal with steel connections around the membrane structures using IDEA StatiCa software. Right, and I prepared a introduction presentation to tell you a little bit about what is IDEA StatiCa, what we do, and the story and the software that we have. And then I will basically continue with what Gary has started. So I will use the same data that he just showed you how to export from ixCube. I will take them and continue the workflow in IDEA StatiCa. So I will finish with all these connections designed, checked, and with printed out report. Basically all that you need to do in your job, I guess. All right, so let's start with what is IDEA StatiCa. So who we are? So we are a software house. We are based in Brno in Czech Republic, and what we do is basically we produce software for structural engineers, and we focus on these special things like steel connections, concrete details as well, and stability of members. Here you can see some numbers. Currently, we have about 11,000 customers around the world, and the company is about 120 people. Bigger half of that are developers that code the software, and then we have a team of structure engineers. I am the member of this team that do these presentation, technical support, etc. And the company is a independent family business, and it started about 15 years ago. Before that, the core team of developers and the founder of the company worked in the software field already, so there's plenty of experience. And what we are proud of is that part of the company is, or a lot of employees of the company are structural engineers with experience from practice. This is overview of the map. We have a couple of offices in Europe, US, and Singapore, and this is the coverage of our users around the world. And why do we do it? What is our goal? Is that we want to enable structural engineers, designers to design structures with ease. So simply use less time and be safe. And what kind of software do we do? So we focus, let's say, on 4 main fields. The primary field is steel connections. That's what we are famous for. But next to that, we also can solve general members and its stability and buckling problems. And we also have our concrete department where we focus on discontinuity regions, concrete foundations and blocks. and things like that. So another specialties that are very problematic to solve with the standard finite element tools. And also we have department for the data exchange that you see today. That's for the BIM links and data handling, etc. All right, and basically where we are positioned in the tools that structural engineers use or design offices use, typically you would have some FEA solution like ixCube. Oh, sorry for the typo. Then you have a CAD solution like Tekla or AutoCAD or something like that. And then you need some tool to do the code checks to prove that the requirements of Eurocode, American code, Australian code, Indian code, whatever code, that your design is okay regarding connections, details, etc. And for that is what you need IDEA StatiCa, and these three segments complete the whole package. That's all what you need to do your job. That's how we see it. Now, this graph kind of proves that we do this right, that we have this exponential growth of our company. This is number of seats. That means how many licenses we have distributed or sold around the world. And this is very nice for us. We are very proud of this. So that's why I want to show this. And why should you care, or what is so interesting in our solution is that it's so sufficient or successful because of this CBFM technology. This is how it all started about 15 years ago. That's basically a synergy of the component-based method and the finite element method. So at that time, our developers put heads together with university professors, and they developed this method and then used it inside IDEA StatiCa software for the calculations and code checks. So that's the heart of our software. It has been developed and verified by many universities. There are many verification articles, laboratory tests, etc. All of that is on our webpage, as well as published in these two books. Next to this CBFM method for steel structures, we have invited also CSFM method for concrete structures. That's another story. And for example, the CBFM method, it became already a general solution comparable to finite elements in the history. And it has been already adopted with our cooperation with Hilti, for example, in their Profess software, and some of our already existing competitors, to be honest, such as Global or CIPE or other software houses, that they already are using CBFM as well in their ways, in their tools. All right, now what do we do around steel connections? That's the main topic for today. That's what we are mostly interested in. Basically, IDEA StatiCa and its application named Connection. Here you can design, calculate, and code check such a complex connections. So this is the biggest advantage of our software. There is or there hasn't been any tool like this to solve these complex connections. But next to that, we already caught up with designing very effectively, very quickly, the standard connections as well. And for that, we are using the data exchange via BIM links, and we use the bulk design and bulk calculation. That means if you design only one connection and all the similar connections in the structure are automatically designed and calculated as well. So this is super fast for, let's say, some standardized structures, right? And you can also solve these footings and anchoring and this connection application. What is the very nice advantage of this software? It's based on finite elements. So we can see in the results, not only the code checks, that means if your bolt, for example, passed the tension check or something like that, but you also see the stress flow, the deformation, the strains. And this is a great, because you get a picture of what is going on in your connection, in this detail of your structure, and you as a designer can react on that. For example, here you can see as the concentrations, you can strengthen the bolt assembly here or whatever, and on the other hand, you can maybe use less bolts here to have your design optimized and economical. That's a great thing. Next to the standard stress strain analysis and the code checks, the software also allows you to perform different analysis types, such as buckling analysis. You can do a stiffness analysis to classify your connection and know the initial stiffness that you can use then back in your global structure model. You can see the overall capacity of your connection and also use the capacity design for as a part of the seismic assessment of connections. And of course, you get the code checks and reports for all your calculations. Now, next to these analysis types and what connection can design, you have these BIM links. So that's the data exchange. That's what Gary just showed you the first part, how to export from a global model from ixCube to IDEA StatiCa. So that's the data. Then what you will see more today is the third step, that you design the connections, calculate them and code check them. And then what you can do is you export the data for detailers or other people involved in the project. And this accounts for the global analysis software data exchange. What you can do is you can also import data from your CAD model, for example, Tekla structures or advanced steel. Here it works the very same way. You get all the data, but obviously from CAD software you don't have any loads, any calculations. So this is something you have to add from either manually or import from some Excel sheet, or you can merge the data from your FEA and CAD models imported, and then you get the results and reports. And there are also some segments that we can also cover as well with the software, and that we have proven in a project from our customers that it is usable. That is the oil and gas segment. So there, it's important to calculate the buckling of hollow sections. This is of course possible with the CBFM technology. For seismic regions, we have this capacity design to prove that the plastic hinge and the behavior of the connection is within the designed range. And another very nice application is that you can design the anchoring, and then because in this connection, as you see here, this application connection, you design the anchoring into the concrete block, but it is not possible to add the reinforcement in the connection app. But what you can do easily, that you take the data and open them in our second application, which is called Detail, and that is focused on concrete structures. Here you can add the reinforcement, and this supports the 3D volume finite elements of the concrete, and you get very precise nonlinear analysis of the concrete with the anchors and the concrete cone, etc., with all the checks. So this is very helpful in case that your anchoring is, for example, some special cases like very small concrete blocks where some code checks like the concrete cone typically fails, and you need to prove that it's okay with the reinforcement. All right, you can also use parametric templates to even simplify or speed up your modeling time in the software. And you can also use API for those fans of this technology. So we have completely opened API for our software, so you can use any tool you like. We also have special API prepared for Rhino and Grasshopper workflows. Everything is documented on our developer site, so you can download the codes, you can see the tutorials, and do everything on your own. All right. So that was about steel connections and all around that topic that we have. Now, just shortly about steel members as well. This is something that's wrapped in our member application. And this is a tool to assess the stability of these sometimes complex members or sometimes simple members with complex loading scenarios, right? And this member with CBFM technology, it's powered with the geometrically and materially non-linear analysis with imperfections. So that is the most advanced analysis you can do today with softwares. And all of that is in a very simple interface that you can very fastly design any member and analyze its stability. So we can see some examples. There is very big freedom in the shapes and loading scenarios, whatever you would like to design and analyze. And what it does basically, you calculate the buckling shapes with the linear buckling analysis. You can see this is typically the buckling shape number 1, typically buckling shape number 2, the sinusoid, buckling shape number 3. And again, the great advantage of this is the visualization, that you can very fastly, you see what's going on with your member. Next great advantage is that you design the real connection shapes, and the program takes into account the stiffness of these connections automatically. So then you can experiment with that and see how your member and its stability reacts on different types of connections. So here, obviously, the fin plate is much weaker and softer than this end plate with wideners. So the buckling factor is lower. That means this is higher risk of losing stability of this lateral torsional deformation. All right, that's one thing. Another thing is that you can do all sorts of openings and stiffeners and things like that, play with that, and again, optimize your member, which is at risk of losing stability or is for some reason critical for your structure. All right. How it works is that in the member, you calculate the materially nonlinear analysis. This is what all standard FEA solutions do. Then the linear buckling analysis that shows you the buckling shapes. And then what you do is you choose buckling shape, which is the critical for your structure or most dangerous. You add the imperfections and you calculate the nonlinear analysis. That simply tells you if the member is okay or not okay. Right, so that was for the member, and I will conclude this introduction presentation. IDEA StatiCa, that's the software that would help you save time in your work, and that means money, of course. With that, you can design and code check anything, all kinds of connections and members as well. You can do this very fast, and you can deliver your projects completely. All fine. And this is something just to point out that we established a very straightforward partnership with the main software houses with, let's say, bilingual respect to each other. So we cooperate with each other on the data exchange, etc. And these are some of our clients, just to a little bit show up. And that would be it for the introduction. And I will now jump right into the live demonstration, okay? I'm not sure if I should give any space for any questions or any reactions for the intro or not.
If anybody has a question.
I think it was
quite
clear.
Okay.
And we will save the, by the way, we will save the time for questions and answers, ideally at the end of the demonstration, and we can discuss your questions, and I can answer them and show you what you need to know more. All right, so now the practical part. So how to design connections with IDEA StatiCa. So basically there are three ways how to start. First way is you start from scratch. You just open IDEA StatiCa software, you start a new project, create connection, calculate it, and you're done. Or the second option is you use BIM links. So you start with some data exported from some FEA software like ixCube. Then use the Checkbot app and connection apps to do the design and everything. Or you can use the API workflows, Grasshopper, and you can code and prompt your workflows and automate, etc. Right, so from scratch, just briefly, if I show you that, if I install IDEA StatiCa on my computer, I launch IDEA StatiCa. This is the welcome screen. You can see some settings, some news, etc. And here you see the list of applications that you can run, right? So if I open connection first, that launches the IDEA StatiCa connection app. And I'll show you just in 1 minute how it feels. And then we will go to, to the data exported from ixCube. So this is IDEA connection. When you start it, what options you have here? You can select some starting template of some shape, or if you don't like any templates, you can create blank design or completely blank workspace and start from scratch. So I don't know, for example, if I select some design here, you can select the design code. So this is what we support for now. And that's it. So if I create the design using this starting template, then what I have is the model. This is the main modeling screen. I'll just try to move the panel of my Zoom app. Okay, right. I was in my way here. Sorry. So here I can change the parameters like this. And play with this template. Or what I can do is I can explode this template and I can turn on off these operations. And if I don't like this design, I can just delete it and use these list of predefined operations to basically model anything. Again, I can play with position and vectors of these members. I do whatever I like. So basically, here you input the internal forces. So just quickly, if I calculate this, now you can see it gives me error because This is a very bad design, so I'll just leave it like this. That would be better. Now, this is the calculation. That's pretty fast, and you can straightforward see the result. Basically, everything is green here. If there's something failing, then it's colored in red. Here we have the check tab, where you can see the stresses, the mesh, the deformations, and you can review the results. I can show you that a little bit more in details with the real example that we have from our membrane construction. And the last step is obviously to print out the report that you can save to PDF, doc format, or whatever. All right, so that's basically the workflow from scratch with connections. So I will close this because we are not interested in this today. Just wanted to inform you about that. What we are interested in is using the data imported from ixCube. Great. So what you have seen is how to export the data from ixCube to be ready for IDEA StatiCa. Okay, so Gary just demonstrated that, and he sent me those data. Let's say I am his colleague from another department. I am responsible for the design of the connections of this structure. So he sent me the data in a zip file. This is here. This is the data. And what I will use is I will just extract the top mast. And this is the data I need for IDEA StatiCa. So, well, it's already here, so I'll replace that. I have it already extracted. So this is it. This is the folder that represents a Checkbot project. So I will now start the Checkbot app. It's here. And I will open the project in this folder that I got from ixCube. All right, so this is my Checkbot app. I will create a new project. I will name it ixCube export. Again, I can choose the material of my project, which is steel. I can choose the code. I will use the Euro code, and I create a project. Good. So now you see the checkbot. It's blank. There are no data. So what I do is I will open this this folder. So I'll navigate to my desktop and open this top mast. All right. So you see there is the whole part of the structure, the mast, and these two cables. You can see the nodes here, 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 and here. And if I maximize this, you can see the list of the nodes I have imported. Here you can see only one. That is the top mast node. But once you export one node from any FEA software, you export the surrounding structure as well, and the end nodes of the surrounding members. So the data that you need for these connections, for these nodes, are included as well. And there is a simple trick how to add these connections to my list of design items, is that I use this add connection. I select these nodes that are empty now. I will press spacebar or right click or enter. And now these nodes are populated with connections. So you can see now I have these little cubes that represents connections that I can then open in IDEA StatiCa connections and actually create and calculate the design and do the code check and everything. But before that, I want to show you a little bit around the checkbot, what you can do here, it's basically a very simple manager of the data. So here, what you can do is you can also export the data from here. Show you that at the end of the presentation. Here you have options for conversion. So sometimes in the source data, there are, for example, some cross sections that are not automatically recognized. So you can map any cross sections to the library with inside IDEA StatiCa. So these are the libraries we provide for you with most of the cross sections that are produced and used in steel structures. All the same for materials, etc. Right? So this is kind of mapping or conversion between the FEA data and the checkbot data. Usually everything is automatically imported and mapped, so you don't need to use this conversion just in case. This is the display of labels, etc. This is how to work with the current selected connection. Open it. You can also regroup these here. I'll show you that now. So you can see I have now 3 types of arrangements. That means types of, let's say, geometries. So that means how many members are meeting in one node. So this arrangement 2-1 means there is 1 member with this vector and 3 members connected around it with the vectors, etc. So this is automatically identified and sorted into groups. What you can do is you can change the view of the groups, let's say to simplify it, and you can create groups like this. Oops, sorry. You can create groups within one arrangement, right? So if I want to create a group, for example, these are the 2 anchorings of cables. So they have similar geometry, 1 cable, and that's it. But if I would like to make a group together with this mast base, then it won't let me do that because that's completely different geometry. Why is it so? Is because you will see that later. If I create a group, now it's here, I can create group with 1 connection here as well. Why we have these groups? That's because it's very beneficial if you have many similar connections. Then I have only 2 here, but imagine I have 50 connections of the same geometry within a project. What I then do is I design only 1, and the design is adopted by all connections in the group, and I can calculate it then all together. So that's then super fast how to deal with the groups of connections. All right, so I will simplify my view now to groups only. This is, I just like it more, so it's simpler. And of course, you can then regroup, so you can, you know, remove any connection from a group, create new groups as you like. Yeah, you can rename the groups, whatever, cable anchoring, for example. All right, so that's a little bit playing with groups and sorting your data, renaming them, etc. Then what we have here is the overview of the imported loads. So once you export data from FEA, that exports the load cases and as also the combinations. So this is the data that you have provided, and this is the data, usually it's automatically the combinations that go to the calculations in IDEA StatiCa. All right, so I have these 10 ultimate limit state load combinations and their results imported. If I like, I can remove any of these and again reshuffle. I can do whatever, yeah, create my own design group of loads, etc. But by default, it is not necessary to do anything with that. Basically, you want to code check your connections with all the combinations, right? All right. Then there are some possibilities to merge members. That's, for example, is not useful here. If you have a long member divided into 5 pieces, you can merge it here. You can also merge if you have very close by nodes imported, so you can merge these nodes into one and design it as a complex connection. What I can do here as well is to draw the internal forces. For example, yeah, there are no moments, of course, so the normal forces, and I can check the values that I imported from my global model. And that's basically it. For the checkbot here, you can change the view, and that's it. All right. So now we know how to handle the checkbot app. So let's get into designing of the connections. I'll just check my presentation. I have some slides to follow and to show you when the time comes to jump out from the software to the presentation to explain you some details. But then the first thing is I want to show you is when you import the data, of course, the materials and cross sections are imported in the materials tab. And here, the specialty of the membrane constructions, of course, is the steel cables. That is a little bit, let's say, specialty for our software to deal with cables. So the cable is replaced by a solid rod of the same diameter, and the material properties is imported like this. So what you need is sometimes you miss the correct values, and so sometimes you have to modify this special material imported. So I will do that. I want to have these values of the strength of the steel for the cable, the yield and ultimate. So let me show you how to do that. Go here to materials, click steel cables, and here I simply rewrite so 1800, and I will edit this to 1500, right? This is the thick plate properties. So I will rewrite that as well. Of course, you can use any numbers or values that you feel fit. All right, that's it. And now I'm ready to go to design the connections. So I will start with the top mast. And I will open it. Now the connection application opens. And you will see that I have all the data I need for the design. So I have the geometry, the mast, and the cables here. And I have my internal forces imported. So the normal forces and shear forces for all the combinations. So I can review them like this. All right, so I'm ready to start to do the design. How I do that, I use these operations. So I have this set of manufacturing operations, such as cut and plate, splice, etc. And we call them these 3 rows, we call them like the predefined operations. They basically create with one click many things, right? So with one click you create the plate, the bolts, the welds, the cuts, and everything. So that speeds up the design process. Or if you like, you have here the list of the general operations, and these actually do just one action, like you create one plate, or you create one bolt, or you perform a cut of plate, something like that, right? So I'll show you how to use them to do our design. And what are we actually going to design? That's important, how we want it to look like. So this is my, let's say, draft of the design. This is what I want to
Can you change the
achieve.
blue? It's a little bit, it's not so visible. The blue color? No.
I'll
the
try.
color of the layer, I think. What layers?
Yeah, I know. I'll try to do that. Because I really
You don't know how to get.
I really forgot how to work with without.
It doesn't matter. Maybe layer properties. Yeah, this is layer
Yeah,
00255.
these. Okay.
Match properties. Measure where.
Sinistra, layer.
Oh, that's for the single line. Where is layer property? Layer properties is there. Layers on the left, you have layers.
Yeah.
Layer properties. Yeah, that's
okay.
it. Choose the layer. Yeah, that's it.
Okay, let's see.
I think you have to say okay, no?
No.
Apply, maybe.
I don't see that.
The green.
I don't know.
It's also for me. I mean, anyway, don't worry. Come on.
I can do it like this, maybe.
Don't worry. Yeah, if you zoom in, it's quite visible.
Okay, let me close this.
Yeah, that's fine.
Is that better?
Yeah.
Okay. So basically, this is the mast. There is a cup plate and a tube welded on this, and another cup plate and the connecting plates nicely shaped. And here are the holes for the pins that hold the instruments for anchoring the membrane, of course, and the cables. All right, so this is what I want to do, and I'm also provided with these drawings of these plates, and I will use these to import them to IDEA StatiCa, right? So if I can show you that, I have this folder where this is the drawing. I exported each of these plates into separate DXF file. So I have them prepared for the import to IDEA StatiCa. But I will show you in a while. But now let me start modeling the design, right? So first thing is I will add a stiffening plate operation. And so I have some general plate here, and here I have these properties of the operation. So I can change the thickness of the plate, I can change the size and its position and its tilt and everything, right? So what I want to have is a 15 millimeters thick plate. This plate is circular. Its diameter is 95 millimeters. And I want it to sit on the top of this tube. So I will choose the member LCS. And I will choose this member. And now you see It sits on
How did
that.
you do that?
Sorry?
How did you do that? Repeat it. It was nice. That's the member local coordinate system.
Yes, here.
Okay. And then
So
you click it. What did you click there later?
yeah. So first it looked like this, right? So
Yeah.
origin, I say instead of joint, which is the general position in the workspace, I change to member local coordinate system, and I say the member is this one,
Fine.
okay? Or I can
Right.
choose also from the list. I see the label. This is B102.
Yeah.
So like this, okay? So now it's here. And the last thing is I want to move it down to have space for the top little tube. So I use minus 220 millimeters. And now it looks like this, okay? All right, there is one message, some error message that it is not possible to weld SP1. SP1 is this plate. And this is because when you choose to member, it also wants to create a weld between the member and the plate. Okay, but this time I don't want the weld to be created. I want to edit manually. So I switch back here and the message is gone. And now I will cut the tube and weld it to the plate with another operation, which is the cut. Okay, so I'll choose this. And now I need to choose which member I want to cut. So again, click B102 and cut by. It now shows me members, which is the default selection, but I want to cut it by a plate. So I switch here to this icon. And now it automatically finds the nearest plate to this tube, which is the SP1, and cuts the tube and also adds the weld at the same time. Okay. So this is pretty straightforward. What I need to do, or what I like to do, is change the thickness. There are no flanges for a tube. Okay, so I turn this off. It was already turned off, obviously, but I like to have. I'm very punctual, so
Yeah.
I want to have this perfectly nice. And here I simply change the weld thickness 20. So I'll choose 5 millimeters weld, and I can also choose the material of the weld. The default material for my project is this steel 275. If I like, I can also change the material, add new material for weld, for plates, whatever. I can also define my own user-defined material. Yeah, that's what you have seen in the materials tab. This is now disabled because I have the connection open. If I close this window, I will have the materials enabled for editing. Anyways, get back to here. So first step done. All right. The next thing I want to do is I want to add this tube on the top. So another operation, and that will be the stiffening member. All right. So stiffening member is added, and automatically the program selected some cross-section from the list of the project, but I want to add a new cross-section because my tube is, if I go back here, I don't know, this says tube 88 millimeters thick of diameter, sorry, and 4 millimeters of wall thickness. All right, so I select the tube and input this data, and the steel material is not the steel cables, but S275. Click OK, and the tube is in position. Now, what I can do here is I can define the length of the tube. So what I will use is, you can see the dimensions here in the workspace. I will define it like this. And now I need to put it in position. Now this is a tricky part.
Sir,
Okay,
why is it come from center? Both side offsets.
yes, the offset is that you can move the stiffening member in space, right? So
No, why is it starting from the center?
okay, why is it
Oh,
here?
yes.
Okay, because
Yes.
this is when we are in
Origin
the
of the node.
workspace. Yeah, this is where if I switch to here to transparent mode, you can see the black ball, and this is
Okay.
the center of the node, right?
Okay.
This is this place.
Right.
So that's the zero of the global
That's
coordinate
the zero.
system.
Okay. Okay.
So
Got it.
I
Thank you.
added. Yeah, you're welcome.
Yeah.
So
Yeah. Thank you.
welcome. So every object I add, stiffening member or a plate or whatever, it's by default set into the zero of a global system. All right.
Right.
Now how to position it, right? So here you can add the offsets and you can add the angles in space. But obviously this is very sometimes very difficult because this member here, we can see the vectors of it, and it is oriented in space. And what I did, the trick with the plate is that I use this member LCS, but in the current version, it is not possible to use this feature for stiffening members, right? we will add this because usually we work with, let's say, standard steel structures which are perpendicular.
Yeah.
And for the membrane structures and the tilted masts like this, it's kind of special, let's say.
Yeah. So it's a good input even for you.
Yeah. It's a. By the way, this was when I was preparing for this webinar, I was very excited because that was the first time I designed connections for membrane structures. I didn't have a wide experience with that. So I gathered a couple of tips how to improve our software, and I passed it to our developers. And we will in the coming versions we want to implement that. And that is, for example, working with stiffening members and the local coordinate systems of members, so I can position it easily. But since I don't have this feature, so how to do that, right? So I need to find these angles and the positions, right? And I'll show you a trick how to find the angles of this tube, so I can copy it to the edit tube. Right, because here I see only the vectors. I don't see any angles, right? So what I do is I go to Checkbot, and there is this export feature. So I can export this single connection to outside. Yeah, this asks me to close this window. So I say yes, this is now saved. And I now export this node outside the Checkbot project. So export one. Oops. Okay. Now, if I minimize everything, this is now here. This is a single file. And now this is, by the way, a useful thing. If I want to, for example, if I have a project, I want to export one connection and send it to my colleague or whatever, I can do it like this. I have this single file, which is, by the way, I want to show you it's very small in size, so it's easily attached to any email or WhatsApp message or whatever. Yeah, and then if I open this single file, you can see this is now in a connection outside the Checkbot. And if I click here, I can see now, I can choose the display, okay? And I see the beta, the direction angle, and the pitch angle, okay? And with this, I can now read it, and I can use it for my design here. So that helps me to identify the angles that I need to input.
I have a question.
Sorry, this is already finished. Yes.
Before doing the cut,
Mm-hmm.
didn't you see those angles?
No. Because
this is
because
what
you
cannot
see.
change it.
You see the vectors.
Yeah. Okay.
Mm-hmm. All right. What just happened is that I forgot to save my previous work, so I will quickly do that. So very fastly again. Oops, sorry. All right. I turn off the weld here. So little repetition. Radius 95, and this was minus 220. Then I add the cut by plate. Okay. Now the stiffening member. Here I add the tube. All right. So now I identified the angles, so I want to input them here. So this was minus 135 and this was 72. And now you see this nicely matches the axis. Okay. So this is a little workaround how to position a stiffening member. And I will also move it in space towards the cap plate, and I want to make it longer, right? All right, so now let's continue. What I will do is next is that I want to cut this tube by this plate. So I can take advantage of the copy function and copy this cut operation, and I only change the member from this to this, and everything is already set 5 millimeters well.
With the plate.
Yes,
And
exactly.
no, the positive side, he keeps the positive side of the member.
Exactly. So if I switch to
the direction
transparent
of that
mode
one goes
here,
from bottom to top.
exactly.
Yeah.
If I switch here to transparent mode, I deactivate the operation, now activate it. So you can see it's cut.
Yeah.
And the yellow line is the weld. All right.
How did it know which side to cut?
You said it here. Let me show you. I will just do the same for the upper part, and then I will switch. So you will understand how this works.
Okay.
So what I want next is I want to create this cup plate on top. So again, I will copy this one. Okay.
Sorry, where did you copy it? I lost you when you copied it.
Yes. So I choose the plate. I can click on it on the 3D scene or in the tree. And I have now few options.
Okay, there's a copy.
Click
Okay,
here, or there is the copy here on the top of
the copy was hidden for.
Yeah. Okay, so copy. Now you see the overlapping plate, and what I will do is so here, and I want it a little bit higher by 10 millimeters, like this. And I want it smaller, of course, so I change the diameter to my project size. All right. Now let's get back to the other cut. So again, I can click in the tree, or I can click also, for example, on the weld, and it highlights the operation in the tree. And again, I copy this operation, Okay, and now I say I am cutting still the stiffening member SM1, but not by stiffening plate number 1, which is this one, but by stiffening plate number 2. So I change it like this. Okay, now it looks like this. And now you see this is the answer to your question.
Yeah.
Now it cuts the other end, right? This is what I don't want, but I simply switch it here. So cut me the end part, not the beginning. Okay, so for this stiffening member, here is the beginning, down here, and up here is the end. Okay, you can see it also in the local coordination system that you can turn on here. All right, so this is okay. The first part is done. Now I will add these plates that I have prepared in the DXF files, as I showed you. Okay, so this is my top mast left plates, right plates. These are okay. This is the right plate, and these are the
plates.
On the left side are the left plates. They are the same size and shape. Okay, so if I go back to the global model to revise for you, this is the right plate connecting to the membrane, and these are the left plates connecting to the anchoring of the cables. Right, just for sure, I save my data, and let's import the plate. How you do it is I add the operation, I choose the stiffening plate, right? So again, I have some general plate here. By the way, the program tells me there are some clashes. So if there is plate going through another plate, it's clashing. So there is this warning informing you there is something wrong. And now let's import the DXF. So how to do it? In the shape, I switch from rectangular to polygon shape. Okay, choose this. And now it shows me I can import the polygon from DXF. So I push this button and I navigate to the desktop, to my folder with DXF files, and I choose the top mast right. All right. So this is the shape of the plate. What I do here, I can switch between millimeters and meters, depends on the scale of my DXF, but it's in millimeters, so I don't do anything. What I do here, I click on the line. It highlights the part of this continuous polyline, and it depends. Sometimes the DXF is one full line, sometimes it's exploded into single lines, all right? But it doesn't matter. What you do is that you push this consecutive and it connects the whole shape together. And then you say, give me this outline to create the plate. You can see it here. This red cross represents the origin of the plate, so the 0 of the local coordinate system. And that's basically it. You click OK, and you have the plate in position. Well, it's not in position, but you have imported the shape.
You have
Yes?
this kind of templates ready in your stock, in your library.
Well, there is a template library. I can show you that maybe a bit later. It's here, but the library is not for the plates, but it's for the whole connections, right? I will show you it with another example. So basically, you save the design that I'm just assembling. Yeah.
Okay.
I'll show you it with the later with the anchoring.
Sorry,
Okay.
you bring it in without the opening. You don't bring the opening. the plate opening.
Okay, but to have a
You don't bring it.
but there is no library for, let's say, single plates. All
So
right.
you have made this kind of plates for this.
Yes, I
Okay.
have the drawing,
Yeah. Okay.
the preliminary design of my structure. I have the drawing. I have it
Okay.
here, and I only selected this and create a new.
Is it possible to draw like these plates in this, or we should import only?
Well, it is what you can do is
Mhm.
if I create another plate, let's say, is that you can shape it, of course, with the size,
Okay.
and you can also go to editor.
Okay.
Oops, sorry for that.
Mhm.
Shows me error. Ah, I see. Oh, this looks like a bug, but let's see. I'll just
Save this.
save it, close it, and open again. By the way, you can see now the image.
Right.
I think, yeah, there was some small bug working with the checkbot, so I just restarted. Oh, in the editor of the plate, once again, it's on the right click and editor.
Mhm.
Here you can do this operations like roundings, and so shaping the plates like this, adding holes. So this is one option. This is, let's say, a simple editor.
Okay. Okay.
Or if you choose the polygon, I think there is it is not possible to. I mean, there is no drawing tool inside IDEA StatiCa, right?
So we
So
have to import the
you have
what
to
we have the
yeah,
drawings, right?
you have to
Okay.
prepare it in some
Got your
CAD.
points.
You have
Got your
to
points.
yeah.
Okay.
You have to
Continue,
do
please.
the
Thank
drawing
you.
in some CAD and
Yes.
then save it in the DXF format and import
Okay.
it.
Okay, sir. Please. Thank you.
And you
Welcome.
cannot import it with the opening, right?
I think you can. Let me try that. Also opening. You can put it in. So I'm thinking if I have some DXF with opening, there is not one, but let me create quickly one. So a new file. Okay. I save this as DXF to my desktop. Okay. I close it so I don't block the data. And now desktop, drawing one. Ah, okay. Ah, here's the opening, but I don't know what happened. Probably it was, probably it somehow connected with the other. So let me explode it.
Should this in block?
Probably, yes. Explode, right? So if I unblock it, now let's save it. Oops, so that was DVG. XF, okay. Okay, one more try. No, for some reason. But
It seems,
yeah, but I think you can do it. I think I experimented with this. It's quite unusual because usually the openings is for pins and bolts, and you do the model, you create the openings or the holes when you add the pin or bolt into the plate. Yeah, I'll do that in a minute. So I'll show you that. But anyways, I can also this editor. I can show you how to create a hole in this plate with the editor as well. So it is possible to do that. But for now, I will continue positioning this plate. Okay. So I imported the shape, and now I want to place it here in this position. So I will use the parameters here. The thickness is 10 millimeters. That's correct. That's what I want to have in my project. And now I will again choose this feature, this origin, and now I will say place it on a plate. So place this plate on a different plate. I want to place it on the SP1 plate, which is this one. Okay, that's correct. But I wanted to turn it around, of course, etc. So let's do that. So it's a rip of this SP1, that's correct. And the location is not front, which is this side, but the rear, which is on this side. Okay. So now this looks much better, right? And I need to move this plate a little bit outwards so I can move it with these X and Y coordinates. Exactly. And by placing this plate, which is SP3, right? This is the SP3 plate, and we placed it on a SP1 plate, which is this one. It also automatically creates the weld.
The welding.
Yeah, I can turn it off, of course, or I can set any weld I like. For this case, I want a double fillet weld, so it means on both sides. And I will again set the size of 5. If you leave 0, by the way, this is the default. That means the program automatically chooses for you. Depends on the thickness of these plates. Yeah, but it's better to have it under control, of course, and input the size what you like. All right, so now I have the plate in position, and what I want to do is I want to add the weld here between the weld and the tube, and also cut it here on the top, because we can see the red is the clash. That's the warning here. So you can see in the detail, this plate goes inside the cup plate. So let's cut it. For this, I will use the operation cut of plate. Okay, so
Sorry, a question, Adam.
Yes.
So you suggest to draw the plates bigger, so then we cut them later.
Yes, exactly. It depends on your approach, what you like. Either create the plates bigger, or what you can do as well is not to cut the plates, but set them exactly in the position that you like, and then don't use the cut of plate, but rather use only a weld. Okay.
Yeah.
But my approach
It seems simpler to cut them. That's why I was asking.
Yes, yes, exactly. So what I do is I have this cut of plate operation. So again, I choose which plate I want to cut. It is this one, the SP3. And I choose what it chose automatically the member B102. So you see it's cut on the line, but this is of course wrong. So simply switch this like this, okay? So now if I go to transparent, you can see it looks like this. And the same way I can choose the cup plate, and now, but I have to switch from member to plate first. again, okay, and choose this one, and you can see it's now cut here, and there is the weld edit as well.
Sorry, you added 2 cuts on the same cut.
No. First I showed you cut by member, and then I switched to cut first by this plate. Okay, and I will finish this one, and I will add another one between here. So I just wanted to show you that you can, switch and choose like this, and you see that the clashes are removed here or here. Now the clash still persists between the plate and the tube because I am cutting the plate by the upper plate now. Okay, so now a lot of cuts, but let's find ourselves between these cuts. Now I am cutting the SP3 by SP2. Okay, and I have the weld as well, and I want to have the double fillet weld on both sides. Okay, and choose the 5 millimeters. All right, and now I add. I go back and I can again use the copy. Okay, and I choose from not SP2 again, but I go to member and choose member SM1. And again, I have this cut around. All right, so this way I input and weld these plates. So I will now repeat the same thing for the other 2 plates here. All right, so I can again either create a plate like this or copy this one. That would be faster for me because I have already some settings. So let's copy this one. And I want to first, let me rotate it.
Hi, excuse me. Did you develop to groups some operation to easy copy this kind of?
Yes, there is possibility to group the operations by operation type, by member to which the operation belongs. And what you can do is, I will show you this advantage a few minutes later. You can multi-select and copy multiple operations at once.
Okay, but you can create your own group.
No.
Okay.
This is not possible. It's only the view. Okay.
Okay.
And with the groups, that's maybe by the way a good question about operations and grouping. So grouping is only like the view, right? You cannot create your own groups of operations. It's because this is, let's say, one of the solid laws of or rules of modeling in IDEA connection is that it has to go in sequence. Okay, it demonstrates or simulates how the operations are done on the construction site or in the workshop. Okay, so for example, I cannot add this cut before I add the plate, right? It has to have the logic. Okay, so I cannot move the operations in the tree, so they follow each other. So this is the beginning and this is the end, right? So this is the rule of the connection. It's the sequence and the logic of adding the operations.
Okay, thank you.
And for example, part of this logic is that, for example, if I go this, let's say, this cut, for example, yeah, this one, right? I have the operation cut of plate, which I added earlier than the SP4 plate. So if I look here, I cannot see the SP4 in the list because this operation happened in the time before I edit the SP4. I hope it's understandable and
clear.
it makes sense.
Yeah, thank you.
Okay, and now I show you if I copy this operation and it's after SP4, I will see the SP4 here. Okay.
Now, this is important to understand because it was not clear looking at the. Now that
Yes.
you told us, it's clear that this is an
Yeah.
operation in time.
Yes. Yes. All right. So let's continue with this. All right. So I made a copy of this plate, and I want to change, of course, the shape. This was the right plate, and this is the left plate. Okay. So I go to the DXF shapes and choose the left one. I repeat this and click OK. And now I have the plate here. Again, I have to play a little bit with the position. This is also something a bit tricky, or not tricky, but to position plates in space. You just have to, in this case, play a little bit, but it's not that bad.
Can we draw this connection in Rhino or something and import it, or we have to build it?
Yes. By the way, yes, you can. This was, if I go back in the presentation, this is the type of the cat import, and it includes also the Rhino. So you can create it parametrically in Rhino and import it to IDEA. But then obviously, if you do that, you won't have the load combinations here, right? Because you need the data from ixCube.
Yeah.
It is possible. There is possibility to
merge.
To merge, yeah. How you do it is that you import the data from your cat or Rhino. So you have the finished design. Then on site, you export the data from ixCube, and then with this command, sorry, not this one, but this one. By this command, you choose the file
connection
that consists this connection data with the load combinations, and it adds you these combinations here. There is a tutorial on our website that shows you how to do this, and I will send you the package after the webinar, so you can look at that.
Thank you.
Or just quickly, if I can do that, if you go to ideastatica.com and go to support and learning support center, here you can see tutorials, and there are tutorials for Grasshopper Rhino as well. So how to do it step by step, this parametric design, etc. And there is also this, we have it for Tekla, this merge of CAT model and FEA model into one. Okay, so this is like how to do it step by step, and how to use this command to add the load effects. All right, so that was a little bit side information, and I will continue with constructing this detail. So the last thing I did was I positioned this plate. So it's already welded, as you can see, on both sides. And what I will do now is I want to do this cut here and here. So as I showed, I can do this multi-select, copy these two operations, and say Okay, I need to change, say, this plate and the SP2, so the cut is in place. And the same for this one. So just choose the correct plate. And okay. And I need to change here. Oh, I forgot one thing to show you is the cutting method. Okay. So there are two cutting methods. It's either bounding box or surface. Bounding box is a virtual box that surrounds the member or the plate of the cross section. So bounding box of this tube is basically some virtual polygon around it. And the surface is basically the surface that you see. Okay, so if I switch to this, and this is very beneficial to use the surface if you have some, let's say, spatial or circular or some members or plates like this. And it
Bounding
depends.
box is a straight plane, and surface is complex surface.
Yes, exactly. So it depends what you want to perform. You can choose here. For some cuts, it's better to use the bounding box. For some, it's better the surface. I always say the best way is to try and see, and this way you learn which is better. Okay. All right. So I will just go back here. You can see if I switch here to surface, it moves a little bit. It's very tiny bit. Yeah. So the bounding box goes like around here. So at this point, it's very close to the tube, but at this point on the other side, it's a bit farther, so it didn't do the cut. So that's why it's better to use the surface. All right. Now I will just copy these three and use them for the third cable. So here I want to move this. This is 25 degrees and position it again. Sorry. So in this case, it's minus 14 millimeters. Okay. Obviously, I am prepared. I know what to input here. But what I did, how I did it is I just, I go like this until I'm where at the position that I see it's the best one. Well, there is. Well, the let's say the modeling options are limited if you compare to Rhino or CAT, right? Because we want to keep the tool simple, and we have these, predefined operations and predefined parameters, so that it's easy, it's simpler. And what you can do is you can move it around like this, around the origin and around itself. But that's it for this stiffening plate operation. If you set it sitting on a different plate, right? It's like this. If you, another example, if I have a general plate like this, then I can rotate in around all axes freely, right? But then it's harder to position the plate in space then, right? But it's possible. Okay. So the last thing I did was adding these plates to place, and again I just finish these cut-off plates, the one and the second one. Obviously using the copy function that helps you to be much faster. Just takes 2 clicks and you replicate what you have. All right, so this looks now much better. And the last step would be to connect the cables that are represented by these rods. And I will connect them by pins. Okay, so if I go back here, this is this thing. So for sake of the connection design and code check, what we want to code check is these plates, possibly the pin and all these plates and welds of this connection, right? It is not possible to, of course, code check the instrument used for the cable attachments. You design it using the tables and the provider of the tool, right? So this is out of scope of this program, obviously, but I will simulate it using some simple plates and the pin. So let's do that. So I will first start with this one. So I will add a new plate. Okay. And I will shape it now. So I will make it smaller first. So a small plate. Then I will put it in position. So I choose the plate origin. Now it's somewhere inside the joint, and I will choose this plate. I want to put it on. Now it is a rip to this plate, and I choose not a rip, but give me a doubler. Okay. So now it looks like this, attached to the other plate. I will turn off the welds here. I don't want welds. And I will position the plate where I want it. So position in space like this and rotate it by the same rotation of the rod. Okay. Now the next thing I want to do is I will first I want to shape it using the editor. That was one of your questions, if it's possible to draw the plate. So not a drawing, but you can do the shaping using the editor. That's probably the bug. Okay, that will appear. So let me do this trick. Save the data, close it. That's the fake one. And go back to Checkbot, open it again. I will chase our developers to fix this bug, but that's life. That's part of the softwares, and that's part of also our job. Every live demonstration, something like this happens. But I take it easy. I work for IDEA StatiCa, by the way, for 9 years already, and this just happens, and I'm used
Quite
to
a
that.
long time.
Yeah. It's the Murphy law. All right, so I opened the editor now, and I want to add the roundings. So I will add this rounding, and I want to use the corners that are shown here, the little numbers. So corner 4 is this one, and I want to round it like all around. What I do is, let me close it now. I know that the width, you can see the dimensions here, 40 millimeters on each side from the center. So I can go like this, 40, and I can also input here already at once corner number 3, right? But you can see it creates the rounding on the other side, but not here. Why is it so? It's because I input the rounding, which is exactly the width of the plate, which is too much to create a rounding on both sides, right? It's a strange behavior, but I do it easily like this, just 1 millimeter less, and it's all around. So it's another little trick. Okay, so and now the plate looks nicer. Yeah, just like it more like this. But anyways, so this is the way how I put it in position. Now I want the same one on the other side. So again, I just click copy. I say here, instead of front, give me the rear position. So I have it here. So that was easy. And now I will create another plate in between these two, and I will attach the rod, the cable to this plate. So what I will do is I create a new stiffening plate. So again, it's like this. And I change the size of it. This one will be very small. Again, the origin is by plate. This time by this plate. Again, it's a doubler. I have these automatic welds, very huge ones, by the way. So normally it could look something like this. But anyways, I don't want any weld here. I want it here and I want it inside. And I want to move it outside a bit. So I do it like this. Okay. All right. So this plate will serve as a simulation of the instrument to hold the cable. And I need to connect these 3 plates together. How I do it is by a simple butt weld. So I choose the weld operation. And here I choose one plate is this one. Second plate is either a plate of member or a simple plate. So I choose simple plate and I choose this one. Okay. Now I see the plate is created like this. It's a fillet weld on this edge. You see these little numbers on the edge. That's the numbers of the edges of this plate, right? So if I go to transparent mode, it's better visible. This is edge number 1. Here it's edge number 3, and this is edge number 2. So I put it here, edge number 2. And I have the weld here, and I choose a butt weld, which is the full penetration weld. All right, now I do a copy, and I do the same for the other plate on the other side. And now this is connected, right? Okay, the next thing is I want to insert or attach the cable, the rod to this plate. So a new operation, and I will choose the gusset truss members. Okay, so add this operation. Now how this works. You see something happened here. There is some new plate, etc. This is something I don't really want here. So let's deal with that. This gusset plate operation, first thing I need to do is I want to choose which member I want to connect. That is the cable or the rod. And I will not connect to new plate, which is created by this operation, which is handy if I am connecting, for example, some angle or a tube to another member. So again, this operation creates me multiple things at one click. But at this time, I have already the member here. So I say, give me existing plate, and I choose which plate is that. So it's this one. Okay, so now what you can see is if I go to transparent mode, the cable it's actually welded into this plate, and I will tune it a little bit the way that I want to move the cable to the full length of the plate. And yeah, I want to change to butt weld to keep it simple. Now this is like one piece. Okay, so this is the simulation of the let's say tension instrument to hold the cable and the membrane. And the last thing here I want to do is to create the pin. Right, so let's go to operations again. And here I choose the fastener grid or contact. Okay. So you can see there is some bolt in space, and I will change from bolts to, I have this menu, I can choose anchors, pin or contact. So obviously I go for a pin. Now it wants me to choose which plates. So it will be this plate, and this plate. I can see the pin. Now I can define the size of it. By coincidence, D24 is what I want, but there are also predefined other sizes. Of course, you can define your own size if you like. I'll show you in a minute where to do that. And basically, you can position the pin like this. So now it looks like this. Okay. And that should be it. This is how I simulate this connection, right? So now I'm able to transmit this tension and this little tiny shear force in the cable into the connection and calculate it. All right, now I need to do the same for these two here. So again, what I do is I will multi-copy all this, but let's do this in part because it adds you the new operations here. So it's better not to get lost. Go by little groups, let's say. Now, what I need to do is choose the plate. I want to perform it for this one, which is the SP4 plate. So SP4, and now I can see in the transparent mode where is the plate that I'm dealing right now with, and it's here in space because I need to move it to a different place. Now it's somewhere inside. So like this, 10, and I rotate it like this. Okay. Yeah, that's why it's better sometimes not to do the bulk copy, because for example here it's better to delete these two and copy the one that I just created and just switch here the rear, so I don't have to, change the other parameters that I did already. Okay, and for this one, this should be easy. Just choose this one and this one. Okay, now it's on the other side, so just put it here. Okay, I do a copy of these two welds that I have here defined. That should be also easy, so I copy both of them, and I can also, by the way, multi-select and choose or define parameters here. This is now not possible because, of course, I create the weld for display, but I need it for this one. If I do it, by the way, again, the program gives me warning that I have two welds on the same edge. So let me fix that quickly. And multi-select and weld me to this one. Okay, so these are like the small tricks how to be faster doing these operations. Okay, I copy the gusset plate or the gusset operation, choose here this cable, choose here this plate. That's done. Okay, and the pin, copy and just define these three plates here, and it's done. Here I want a smaller pin, so let's do that. I want a D20. All right, and I want to move it a little bit inside. Okay, maybe like this. All right, so that's done for this part, and now the third copy and paste. So go here. Okay, this is now easier. So can quickly do that. Let's select two welds. Go like this. So you can see if you get familiar with the program, it's pretty fast.
Yeah, actually, it's important that we see the operations. Basically, it's understanding all these operations and what can be done over them.
Mm-hmm. Okay. And now the gusset plate again. So it's this one and this one. Okay, and the pin. So that is the last part of the modeling, right? Now I'm finished. So before I run the calculation, which is here, what I need to do is I need to review the settings of the boundary conditions. Okay. So I go back to the beginning and review the members, right? By the way, it's somewhere in my presentation that I forgot to to go through. So let me review that. I was here, and I want to show you, yeah, this one. So for one bolt or one pin connection, we need to change the boundary conditions because those are typically the members that transmit only normal and shear forces and no bending, no moments, right? And this is described in an article that you can read about how this works, etc. So again, this is on our webpage. But basically, it's very simple. For one pin or 1 bolt connection. I click on the member. I change the model type from the default all 6 internal forces transmitting to the normal and shear forces only. Okay, I do this for all these 3 cables. Okay, and the last thing is there is always a bearing member. This is in this slide. So every connection model, because it's finite element model, it has some, it must have the boundary condition, and one of the members to keep the or to have the equilibrium of forces in the model, you have some, you need to have the support on one of these members, and we call this the bearing member. So a bearing member, it's automatically chosen by the program. Usually it's the first member that you create or the strongest member that create. And sometimes it's a bit random. So again, there is an article that you can read about this topic, and just to show you how it works, how to set the bearing member. Now the bearing member is this cable. So this member, it's shown here on the top of the tab, and also it's visible that the member is underlined in the tree. And obviously the bearing member logically in this case would be the mast, the column. So I change it by clicking here, set bearing. Okay. What
So
it
the bearing
does,
member is the fixed one at the end.
yes, it's fixed at the end. That's, let's say, the support of the whole model, right? The fixity. That's right. And so that's one reason why you need it, and why logically it's the column here. Another thing is that when you input the internal forces, especially if you import them from the FEA, from the global model, for example, ixCube, when you then model the real cat, this is a cat representation, the real representation of the model, right? In the global structure analysis model, it's simplified by basically only the members and the node. But here, when I was adding operations, I was a little bit moving with these members here, which creates a little eccentricities. And because of these little eccentricities, I have little unbalanced forces that are visible here. See? And these unbalanced forces, they are added as reactions to the support, right? So then if I have a perfect equilibrium, it actually doesn't matter where I put the bearing member. But usually there are very small unbalanced forces, and it wouldn't be good to have this bearing member to add these small unbalanced forces, because it can affect a little bit the perfect results. And if I have little unbalanced forces added here, the column takes everything because it's strong, so it doesn't affect my results of the analysis. All right, so setting the bearing member, that's it. And I just save it, and now I can click calculate. That's the last thing I do, or almost the last. The last thing is to print the report. But what happens now is that this CAD model is automatically meshed. So the mesh is automatically created for all the plates, all the welds, the pins, etc. And you calculate all the load combinations at once. So of course, the analysis, the time of the analysis is dependent of the complexity of the of the connection. That means complexity
You
of the
don't
mesh.
you don't set sorry, you don't set the mesh sizes here.
No,
It's automatic.
you know, it's automatic. If you like, you can change it in the settings,
Okay.
but we don't recommend that because the program is verified for the default settings of the mesh. This is the project settings, by the way, and you can change the size. This is the mesh settings, but we recommend not to change it.
To keep it.
Yeah, because if you know what you're doing, if you are let's say aware of the consequences, if you have rougher mesh or finer mesh, how it can affect the results of the finite element analysis, go ahead, but it's better
Do
to
it
keep
careful. That's what you
yeah,
say.
yeah, be careful. Yeah, it's the same as with any finite element software, right? If you play around, you should know what you're doing. Otherwise, you can end in a black hole.
Yeah, absolutely.
Yeah. All right, but this time everything is fine, and I finished the calculation. And let's now review the results briefly. So the first thing I see is the overview results. I see the highest values, highest utilizations of each component in this model with the green marks. That means everything is fine, under 100% of the capacity. That's great. I can see it visually. What is gray is utilized less than 60%. What is green is utilized between 60 and 95%. What is yellow is between 95 and 100%. So for example, this weld, it is quite well utilized. And what is failing, so what is more than 100% of its capacity, is then colored in red. All right, so by this, I have very quick overview, and I can, of course, anytime go back and change anything here and recalculate, right? If I change anything, I will lose the results and I have to do the calculation again. So I don't want to do it now, but I want to show you.
Excuse me, are
Yes.
the pins verified in flexion? Because on Eurocodes there is you can consider a little space between plates, and thus the pin are checked in
Let's
flexion.
see. Yeah. You can review the results in details in the check tab. And here you can have the tabs for each types of components, and here you have the list of components, right? How to orient here is you can also click, for example, in the 3D scene, the pin is highlighted in the row. And one thing, what you can see is the values that are then used for the code checks, this time for Eurocode. So you can see the forces values that are calculated and the utilizations, also the detailing checks. And if I click on this little plus, that reveals me the equations. I can make them, I can scroll down like this, or I can make it bigger. See the preview like this. This is more comfortable. And this is probably what you are asking about. These are the equations that are required by the Eurocode to code check pins. So there is shear resistance check, bearing, bending, resistance check, and the utilizations.
Okay, thank you.
And of course, there are the same data for welds, for example. So if I want to see this most utilized one, I can click on that. I can find it in the tab. Can see, okay, it's here around displayed. I can see the stresses, the normal stress, the longitudinal stress, and the sum of the stresses. Again, all the values here, and again, the similar equations. This is the check Eurocode requires. All right, so this is like this. So this is the part of the results for the code checks, and part of the results for the finite element analysis is here in the ribbon. So as I showed you previously, you can see the equivalent stress. So the distribution of the stress and the concentrations. I can, of course, display the deformations. And I like this very much because it gives me a great picture and overview. If I compare this to, let's say, some analytical approaches or hand calculations, it's unmeasurable. Right, so of course, strains. So I have some plasticity occurring here, obviously. All right, so I think this is pretty straightforward. And the last thing here is the report, but I will skip it this time because I will show you the report, how you do it in the Checkbot, which is better if you have the whole project. You don't need to create each report for each connection. So yeah, but you can do the one report for all connections in the project. Okay, so I save this. Let's go back. So this way, I am finished designing this connection, and I can continue with the rest. So now you can see the time is quite flying, but let me finish this. I will be fast because now what I showed you is basically the principles and how to do things, and I will just do the same thing for the rest of the nodes here, and I will also show you the templates that will make it even faster, right? So let me open this one. And by the way, we are recording this webinar, of course, and later on you can review. If I go too fast right now, you can then review later on in a slower rate.
In slow motion, yeah.
Slow motion, yeah, and click through. So okay. Now what I will do is I will design the anchoring of the mast. Okay, and it looks like, I'm not sure. Yeah, it looks like this. So again, I make this visible. Okay, something like this. Okay, and of course the concrete block under it. All right, so I have the mast. That's the lower end of it, and this will be faster than the previous one. You will see. So I start with the cap plate here, okay, let's start with that. So again, 15 millimeters, circle, member LCS. Here I turn off the weld. Okay, 95 millimeters. Okay, it can go like this, or I can show you a different way this time. Instead of using stiffening plate and a cut operation, that would go like this. I can use only one operation this time, so it's a little trick. I can use a stiffener. A stiffener typically is for eye sections and things like that. But if I add this operation, you can see it looks like this and automatically detects the member, and it chooses the shape as circle if it's a tube. That's right. And here, if I click the cup plate, it does this thing. And I only change the thickness and I say, okay, make an offset here. It's like this, so it's even a bit faster. Change the weld. Here I have welds on both sides, which I don't want to have, so just front side, outside. Okay. So there are like small tricks how to be more effective modeling. But anyways, this is the cup plate. Now let's model the base plate. So that will be this one. Okay. So that will be a rectangle. It will be much thicker, 30 millimeters. The size is 300 per 300. And of course, I need to create space for the connection. So I move it here and I also move it to the side like this, okay? So now it's centered. All right, let's leave it like this now. And another thing is that I will add another stiffening operation and I will create these connecting plates. All right, so I will use again the DXF import. That will be the anchoring cut plate I have prepared. It looks like this. Outline, okay. You see the origin. By the way, the origin of the plate depends on where you, so this is 0, 0 of my drawing. So here is the origin of the plate here, right? So that's part of the, let's say, preparation of the DXF file is where you position. This is because it's then much easier to handle the plate, right? So you know where what to input here. But what I will do is I want to set this cup plate to the stiffener. You can see automatically it detected the nearest plate. That's the one I want. I want it as a rib, that's right. I want to change the weld. Okay. And I also want different thickness. This should be 20 millimeters because it's anchoring. So have it strong. All right. And I want to have it in this direction. So I use this function to rotate it. Okay. All right. That's this. And now the other part. So I copy this. I choose a different DXF. That's the base plate. Okay. Like this. Now, obviously, this is not a good position. This time I want to have it on this base plate. Now, as you can see, this now looks a bit weird, a bit strange, because the weld goes through the base, the plate goes through the base plate, and the welds are here. So I need to a little bit rotate it here. So the location will be actually rear. Right, so I want the plate to be welded on this side, start on this side, and I will rotate it 180 degrees around. Now it's just right. All right. Delete the rotation and that's it. Now, this obviously isn't okay. How to deal with that? I also want to rotate the base plate, right, to be aligned with this cup plate here. So I go back to the base plate and I will add the rotation of it around the z-axis, which is the perpendicular one. So I will go to these 45 degrees, which is the angle of the mast. All right, that looks much better. And now let me finish this plate that I need to move to the side. So I just easily input 20 millimeters, that's the thickness. And now it's perfectly aligned. Okay, now the other side, that's easy, -20, and it's there. Okay, now let's connect this by another pin. So the fastener grid pin. Okay, again, I choose this one, this one, this one. The pin is somewhere here. If I put it to 0. Now what you see is, by the way, the first item is SP4, which is this plate that we see. And its origin of this plate, the local coordinate system, is here, right? Mm-hmm. That's the 0 of this plate. So the positions, if I go by 20, is in the X direction of this plate. The rows is the Y axis of this plate. And sometimes it's you can take advantage of changing the
first
selection. Yeah. So
it does. Sorry, a question. It doesn't matter that these 3 plates are in order.
Yes, it doesn't matter. You can choose the first plate as this one, and the second plate as this one, and it always goes. The pin goes through these 3 plates. It doesn't matter the order, but the order, of course, changes what is the origin. So now I set the SP2, which is this cup plate here, as the first one. So now I will go from the origin of this plate, which is in this case better because I can easily just go to the position I want, just using one coordinate. Okay, and I add a bigger pin, a stronger one. Cool. Now this is looking good, and the last thing is to create the base plate. So I go, sorry, not the base plate, but the anchoring for the base plate, the concrete block. Okay, so there is the operation base plate. If I choose this one, for this operation, the only option is that I can select a member. Okay, the only member here is the mast. And as you can see, this operation is quite complex. It creates the base plate, the anchors, it cuts the member, etc. But it doesn't allow me to switch the concrete block to the base plate. Okay, so how do I do that? I don't use this operation. This is perfect for if you're modeling a single column. But I will use the fasten the grid operation. And here I switch from bolts to anchors this time, okay? And now this gives me freedom to which plate or member I want to create this anchor. So I will choose only one item, and it's the SP4. Oh, sorry, SP2. Oh, sorry, SP3. No, SP1. I'm lost.
A bit tired now.
Yeah, it's SP1. Oh, sorry. Yeah, obviously it's SP1. Now this is highlighted in orange. Why the concrete block is here? Because you set the foundation block, the position block. That's another setting here, right? So you select it here. Okay. So.
Oh, I got lost here. Why what was SP1?
Yes. So this is
An anchor.
SP1 is this plate.
Okay.
Okay. And here you say you want the anchors to be
On the plate
positioned on the
SP1.
SP1.
Yeah.
And the second SP1 is for the concrete block. Yeah. So you can
Okay.
see this is the
Okay. Yeah.
anchors
That was.
and this is the foundation block.
Okay.
Yeah. You can, because sometimes you want to have this separated. For example, you have more base plate on one concrete block or vice versa. So this gives you more freedom to do this independently.
Yeah.
All right. So now this looks better. So what I do here with these settings, I can choose if I want to post-installed anchors, threaded rod or some general anchor, or cast in place, so pre-installed anchors. Yeah, and there are like more options like washer plates, hooked anchors, headed studs, or reinforcement bars, etc. Right? So this time I will choose the washer plate. I select another anchor type, the size and the grade. All right, the washer plate can be circular or rectangular. So let's keep circular 50. Embedment depth is the length of the anchor. And now the positions, again, if I put the rows and position in 0, that means it's in the origin of the plate, which is in the middle, in the center of the base plate. So now I just move the anchor 100 here. There is a little hint, a tooltip. There are few options how I can create an anchor or bolt grid. Yeah. So I can do it like this. So I add like such coordinates, so relative coordinates. If I input a semicolon between a semicolon like this, then it's absolute. Okay, so this is now another one, which I can, sorry, which I can move like this. And I can also add like the multiplier here, like this. Okay, so this is described in the tooltip. And this time I want to do it like this. Plus 100 and minus 100 absolutely. The same thing goes for the position. So I move it 100 here and minus 100 in the other direction. And I have the full grid. Okay. Now this looks much better. And the last thing, I can shape and set parameters for the concrete block. So I can make it bigger like this. Another tip is, or another trick is, I can either have it like similar offset for each edge, or I can use 2 different offsets, or even like 3 different offsets. Sorry, 4 different offsets for each edge separately. All right. So was example, and I will keep 300 and 600 as the depth. That's okay. And the last thing here, which is interesting, or last 2 things, is I can have a direct contact, or I can have a mortar joint, or I can have a gap. So that's the possibilities. So I choose direct, and this is also important, how the shear force is transferred between the base plate and the concrete block. Yeah. So this is up to you to choose. For structures that are heavy, such as steel halls or I don't know, high scrapers or like standard steel structures, it's probably better to choose the friction and to calculate or to design the anchoring, the way that the shear is transformed or translated by friction. For light structures or these cables or whatever, you can choose also a shear lock that can, for example, you can choose also the cross section of the shear lock, typically some I section. So it can look like this to transfer the shear, or you choose the anchors. And now the shear is
Absorbed by the anchors.
absorbed by the anchors. And of course, the anchors are checked per shear, right? So different variants. So I choose the anchors here, obviously. And that's it for the modeling. The last thing, again, the boundary conditions review. So here the only member, there's only one member, so that's the bearing member automatically. And also it's one pin connection, so I need to change to this model type, right? I can show you what it does if I don't. That's, by the way, interesting. I can just calculate one combination. Usually this leads to singularity of the model because the iteration analysis cannot find the final state of the finite element analysis. In some cases,
yeah, because the bending moment it rotates around the pin.
Exactly. So it's like mechanism, right? But in some models, it's like the iteration goes on, like you see now, and it will end
it's catching a little bit of the
because
there's no bending moment.
Yeah, exactly. So
I have a question, no?
But it looks like, you know, it's very wrong.
Yeah, nothing works clearly.
But I switch it, I select all, and I let it calculate. Yeah, go ahead with the question.
See, here we have designed the concrete block, no? If my connection is the cable, one of those cables that generally has an uplift force, the concrete it will tell me if the concrete is going to be lifted.
No, this time no, because let me finish this. I'll show you what it tells you. Regarding the concrete, it assumes that the concrete is perfectly supported. Okay, it cannot move.
Okay,
right. For the uplifting, that's another story, but it's also possible to do it in IDEA StatiCa. Well, let me show you what it shows for a concrete block. I have the similar results as in the previous example, but here, since I have the anchoring, I can see also stress in concrete. And here I have compression force. So you can see there is a stress that goes, that's the stress in the base plate, or it's in the concrete under the base plate, to be precise, right? I can also see the deformation trend is trying to sink into the concrete. I can see on this drawing what is the effective area. That means the contact between the base plate and the concrete that goes in the check, and of course the check itself for the concrete. That's only the compression resistance. Here is the effective area, etc. Right? So that's this. And another piece of information for you is that in this connection, as I said during the presentation at the beginning, the concrete block is simplified. You cannot reinforce it, you cannot work it any further, and it's actually even more simplified. You can see it here in the results. It's only like a plane, which is truly the model inside the finite element analysis. The concrete is simulated as a Winkler subsoil. So it's a plane of springs with stiffness that simulates the concrete block that you define, right? And this is perfectly fine when you design in connections and anchorings and everything. Yeah, you calculate what you need regarding the steel structure and the anchors and the basic check of the concrete, right? So this is okay. If you want to analyze the concrete block itself, you cannot do it in connection, but you can use this button and you open this model, or actually the model of the concrete block, in the application detail. Okay, that was where it was. Just go back to the slide before this opens. That was this slide, right? So I have this in connection and I go to detail. So you can see this is my connection, and this is now the detail app. And in the detail app, I don't have the steel structure. I only have the base plate and the anchors, and I have the concrete block. And what I can do is that I add the rebars, so I can define them, yeah, like this. Yeah, like I don't want to go to details here. Basically, maybe I can show you that in the sample projects. This is what you can download. So then it looks like, basically like this.
Yeah, a full concrete foundation with all the rebars.
So there you add the reinforcement and you calculate it, and
in this case it will tell me that if it's uploaded.
It will tell you in the result. That would take me another several minutes to do this, but there is, of course, the results for the concrete, for the rebars, for the anchors, everything is calculated, and also the uplift. You can see the deformation of the whole concrete block. Here, what you do is that you set the supports. You can set the stiffness of the support plane. Yeah. So you can simulate, you can simulate the subsoil here as well, right? So all that is possible. All right, so let's go back where I was. It was here. So I'm finished with the other node, and I go back to my checkbot, right? So now I see the overview, 2 nodes, all is green, and the last thing is these 2 anchorings. Let's do that very quickly because I prepared a template that I can use for these nodes, and that's another feature. It's this connection library. Yeah, connection library basically is a template system. So if I click propose, it shows me possible designs. Sorry, for some reason I don't see it here. That's strange. Yeah, so if I click on manage, I can see the connection library has three different sets: personal set, company set, and the predefined set, which is part of the software. Personal set is the templates I created and I published into the connection library. So I have few here. The company set is very similar thing that I published, but this is also visible by my colleagues that share the same license in my office. Okay, and I lost the temp. I think I deleted it before. But let me see. I have a model somewhere here. So let me on the site. I will publish.
Can we merge a detail that we have done before with another project? I mean, if I have two files, can I import a node from another file?
That's a good question, and no, you cannot. What you can do is, if you have say a Checkbot project, then you can export, as I did at the beginning. You can export the connections, and then from another project you can export different connections and put them in then one folder or whatever. But it's not possible to add nodes from different projects. Yeah, I mean, yeah. All right. So what I did here, I wanted to Okay, so on my second screen, in the meantime, I published the template into my library because I previously deleted it. So this is how it looks, how it works. So once you push the propose button, it reads the geometry, so the members that you have, and it looks for suitable templates in your connection library. So what is suitable for this one member, this one cable, with this geometry, with this angle, with this vector in space, right? So this is this library. There are some small tolerances. So if this cable is, I don't know, 5 degrees to the right or to the left, I can still apply the template. If it's more different, then cannot. Okay, so simply what I do is, if I click OK, I can review here what is the original materials of the template, what are the materials I want to have. So for example, this is all correct, only here I want to use the smaller pin. So I choose OK. And you see, what I did is basically I skipped adding these operations. So this is also beneficial if you have, in time projects where you use some type of connections or designs. You just save it into your connection library. It stays there forever. It's in the cloud repository, and so on. And what I can do is, for example, if I change here, let's say like this, I add some anchors, and I, for example, make this plate like bigger foundation block. I don't know, change this. What else? I just want to demonstrate.
You can edit maybe.
Whatever, and then I can publish this template and save it either to my personal or company set. Yeah. And then the next time I open a node like this, I have these designs here. Yeah. All right. So basically, this is another way how to speed up your work in IDEA StatiCa. And what I do is I don't calculate it here from this window, but I save it and close it. And I want to show you the work with groups, because now what I did is I designed the connection of this group, and design is applied to all the connections in the group, right? So if I say now, calculate me this group, it will calculate all the connections from here. I don't have to open one by one. So let's see what it does. So imagine in this case, it's pretty easy. I have only 2, but if I have like 100 connections, it's very, very handy. And in this case, something went wrong, or not wrong, but my anchors failed the check. I don't know what's going on, but here it looks all okay. I can review this one by clicking open. By the way, I am missing the picture here, but this is something that we have already prepared for the next version, because we are developing quite a lot our software. So we're adding new things in every version. And here I see why probably it failed, because I see this design is weird. Why is it so? It's because obviously these 2 members have different position and different angles, right? So what I do, it's okay, I can fix it easily. I want to move this, right? This plate. If I click on these operations, you can see they are disabled. Cannot do anything here. Why is so? It's because the logic of the group of the checkbot, right? This is the so-called child connection. This is so-called the reference connection. And I can only edit the reference connection in the group, not the child one, okay? But I need to edit the child one. And how I solve this problem is that I just say, okay, I remove this from a group, and I can now work with it or create another group of this. And now I open and I edit this detail, and I can take a look why it's failing, and I can change the design or optimize the design. Okay, so in this case, I want to probably move it something like this. Oh, minus, yeah. Okay, and yeah, can recalculate here, or I can close and recalculate in Checkbot. But this way, I just finish. Not sure if now the anchors will take it or not. If not, I can, yeah, now it was okay. It was because there was too big eccentricity and there was too high moment on these anchors. All right, so I save it, and this is almost the end. The very end is, as I promised, I go to the report of the checkbot. I can see now all the connections here. I can, add them, remove them, add them. I can also set like the name of the project, etc. I can change the settings of the report if I want to add bill material, formulas, drawings, whatever. I can add a user paragraph here. Oops, that's another bug. But it allows me to write some text and add more pictures. So I want to show you that this report is very customizable. It's custom. You can adapt it as you wish. And then if I generate this now assembles like does the printing of it goes connect node by node, connection by connection, and it prints each PDF for each connection, then put it together and puts the summary at the beginning. This also takes some time, so I can imagine if I have a big project with 100 connections, I can have a coffee.
Of course, more than one coffee.
Yeah. But yeah, here we are. These are the overview results. I can see the groups and the connections in the groups and their status and analysis status. And then I can go through the whole report. You can see it's very long. And basically it consists of all the data, the input data and input of the forces. And also here I can see the checks and the equations, also the pictures and so on. So also the bill of material. So yeah, here I
Nice.
just
Yeah.
what I can do with the report is I can save it to PDF or to doc format if I want to edit, modify the report. Yeah. And yeah, that's basically it.
That was fine. Thank you. Thank you. That was very nice. Any questions out there? They're silent.
Yeah, I think it was quite long, wasn't it? Right? It's like 2.5 hours, something like that, right?
Yeah.
Pretty long demonstration, but yeah, it was just like a full demonstration.
Yeah, I think you have to tell them how they can get the trial version and the license.
Oh,
so
yes, yes. Thank you for that. That's important. So basically, in this demonstration, I wanted to show you and kind of teach you how to do this practically. So now if you install IDEA StatiCa, you can replicate this on your projects and you know what to do step by step. That's why it took so long. I didn't want to miss anything. I wanted to properly tell you that. And I jump back to the presentation. 3 last slides. Regarding the license, you all get your license to IDEA StatiCa by email. You can test it. You can do whatever you want with all the applications I showed you. There is no limitation. It's valid for 2 months. And basically what you get is your username, which is your email, and the password in your email. If you haven't activated the software on your computer and the password expired, you just use this link to reactivate the password. It's just simple. You will get the presentation after this webinar with this link, so don't worry. Yeah, that's it. Okay. After the webinar, I will prepare this whole thing for you. So that's the slides, the whole project that I created. I will share with you as well, so you can open a review, and I'll send you also some more useful things to the tutorials and materials on our website that you can use to learn how to operate IDEA StatiCa and look around. All right, so that's the end.
That was nice. Thank you, Adam. Very clear explanation how to use IDEA StatiCa for calculating these nodes. I think everybody was quite amazed about that. At least I was quite amazed on how nice these details were calculated.
Thank you. Yeah, it was exciting. Thank you for having me on this webinar. I enjoyed this whole project.
Yeah, you did something new, I think. No.
Yeah, it was a good experience.
It's even good for IDEA StatiCa to expand
exactly.
to this different field.
Yeah, exactly.
Okay, then. So if nobody has questions out there, I think we can finish here this session.
Yeah,
Anybody has any question? No? No. They're
If
all
not,
happy.
thank you for your attendance, and I
Thank
hope
you. Thank you.
wish you
Bye-bye.
luck with your projects, and
Thank
enjoy
you,
the rest
Adam.
of the series.
Thank you. Thank you. Bye-bye to all. Yeah.
Yes, that's right. Yeah, that's right. You can do that. There are these tutorials to help you, pick up how to work with that.
So these are grasshopper tutorials.
Yes,
So that's fine.
they say grasshopper, but it's the grasshopper is plugin in Rhino. The same
Yeah. Now we know.
workflow is
We
with
have
Rhino.
used it, so that's fine for them.
Yeah. So I'm not sure if this video shows that, but basically, yeah, you can see now the connection.
So there is a plugin in grasshopper for IDEA StatiCa.
Yes.
That's fine.
So basically, you model this in Grasshopper, and then you just display it, or you just open it in IDEA StatiCa.
Yeah, that's great.
And perform the calculation. Yeah, so feel free to look in these tutorials and experiment.
Yeah, absolutely. I will go and look at them.
You're welcome.
So,
all right. Wish you a nice weekend.
Thank you, Adam. Yeah, and
Thank you.
bye to all.